Imagine a world where atoms don't just bounce off walls like tiny billiard balls, but instead slip right through them like ghosts. That isn't science fiction. That is the daily reality of hydrogen at its most energetic state. Today, we dive deep into the groundbreaking discovery that finally explained exactly why, and how hydrogen switches from behaving like a solid object to acting like a quantum wave. This breakthrough doesn't just change our understanding of physics. It opens the door to revolutionizing how we store energy, power our cars, and potentially unlock materials science in ways we never imagined possible before today's announcement shook up the scientific community. For decades, scientists have grappled with a fundamental mystery in materials science. Hydrogen is the most abundant element in the universe, yet it refuses to behave predictably when we try to store it. In our everyday world, if you push a ball against a wall, it bounces back or stops dead. Atoms should do exactly that. But hydrogen, under specific conditions, breaks this rule entirely through a phenomenon called quantum tunneling. This means the atom doesn't actually have enough energy to climb over an energy barrier. Instead, its wave-like nature allows it to pass straight through as if the barrier didn't exist at all. This discovery changes everything about how we think about containment. If hydrogen can slip through solid barriers, then our current methods of compressing gas into storage tanks are fundamentally flawed because they assume the atoms stay put inside. The new research suggests that the shift isn't random chaos. It is controlled by specific physical conditions that allow this wave behavior to dominate over particle behavior. Imagine a security checkpoint where guards try to stop people from entering, but suddenly the most determined intruders slip through the cracks without ever touching the wall. That is the hydrogen atom in its quantum state, and now we are finally figuring out the keys to lock or unlock that door intentionally rather than just hoping it doesn't happen. Once you understand tunneling, the next layer of complexity involves the philosophical underpinnings of what this actually means for reality itself. Scientists have long debated whether quantum mechanics describes a single objective truth, or if different interpretations yield radically different realities behind the same successful math. From the Copenhagen interpretation to many worlds theory, and even relational quantum mechanics, every school of thought tries to explain how an atom can be in two places at once. The new findings on hydrogen provide a tangible bridge between these abstract theories and physical matter. It confirms that what we perceive as a solid object is often just a statistical average of particles behaving like waves depending on the observer's interaction with them. When we try to measure or contain hydrogen, its identity shifts instantly from a distinct particle to a delocalized wave function. This isn't just a quirk. It suggests that the boundary between matter and energy, or between here and there, is far more fluid than our classical physics taught us. The ability of hydrogen to tunnel implies that the universe operates on probabilities at this scale, not certainties, which has massive implications for how we design future technologies that rely on precise atomic interactions. So if hydrogen can tunnel through barriers naturally, why haven't we just used it all along? The answer lies in control. While nature allows for spontaneous quantum behavior, harnessing it requires a delicate balance of temperature, pressure, and material structure that scientists have only recently cracked. Previous attempts to store hydrogen focused on compression or liquefaction, methods that are energy-intensive and unsafe due to the flammable nature of the gas. This new understanding gives us a blueprint for engineering materials that actively regulate this movement. Think of it like designing a smart filter in a water pipe, but instead of stopping water molecules, you are creating channels that allow hydrogen waves to flow through while blocking them when needed. Researchers are now experimenting with porous structures and specific chemical lattices designed to stabilize the quantum state or force it back into particle behavior on demand. This isn't just about storage, it's about regulation. We can potentially create materials that act as one-way valves for energy, allowing hydrogen to enter a fuel cell but preventing leakage during transit. It turns what was once seen as a barrier problem into an engineering advantage, giving us the ability to manipulate quantum states with macroscopic precision. The practical implications of this discovery are staggering, particularly for the global push towards sustainable energy solutions. Scientists from leading institutions have already demonstrated methods to create hydrogen from water more cheaply and sustainably than ever before. By leveraging our new understanding of quantum tunneling, we can design catalysts that facilitate these reactions at room temperature with minimal energy input. This means we could potentially power cars and factories using abundant water as a raw material without the massive infrastructure overhaul required by fossil fuels. Imagine an economy where hydrogen is no longer a rare commodity extracted from difficult geological formations, but a renewable resource generated on demand anywhere there's sunlight or wind. The ability to control how hydrogen moves through barriers allows for efficient fuel cells that run silently and cleanly, producing only water as a byproduct. This shifts the narrative from scarcity to abundance, making clean transportation viable at scale. We are standing on the precipice of an energy revolution, where the most abundant element in the universe becomes the cornerstone of our power grid, all thanks to understanding what makes hydrogen go quantum. In summary, we've uncovered that hydrogen's ability to tunnel through barriers is not a flaw in nature, but a feature waiting to be engineered. By mastering this shift from particle to wave, we are redefining how we store energy and power our future. The road ahead holds the promise of cleaner cars, more efficient grids, and materials that work with quantum physics rather than against it. If you found today's deep dive into the quantum world fascinating, hit that like button and subscribe for more videos breaking down complex science into clear stories. Drop a comment below telling us what other mysterious phenomena you think we should explore next. Until then, keep your eyes on the horizon. The future is quantum, and it's happening right now.